Hey YouTube. Today's lesson is going to be on force diagrams and how to draw them and what they are used for. So I need you to open up your notebooks, and up at the top of your notebook would you please write a title, Force Diagrams. You don't have to draw the little picture of the airplane, that's just there to give you an example of what a force diagram looks like. And first thing in your notebook, let's do a quick little review. What is a force? Okay, so write this down. What is a force? Okay, let's write this definition down. A force is a push or a pull on an object which can cause objects to change their motion. This is very important because when you change your motion, you are accelerating. We'll get into that later, but basically a force is a push or a pull which can cause the object to change its motion. And next in your notebook, let's answer this question. It should be review for us. How are forces represented? Write that down. So forces are shown by using arrows. Technically we call them vectors. Using arrows, and the arrows are going to show two things. They're going to show the size of the force and the direction of the force. Okay, let's talk about the four most common forces that we're going to deal with in this class, or basically in life. And by the way, if I'm going too fast, it's okay to pause the video and finish up your notes. So let's write this down. The four most common forces, I'm going to go through them. I'll just give you a quick little list, and I'll go through each one in a little bit more detail. Okay, here's a quick list of like the four most common forces that we're going to talk about in this class anyways. First off is the force of gravity. We're all pretty familiar with gravity. Okay, we abbreviate that. We're not going to write gravity out all the time, so we're going to abbreviate it capital F, lowercase g. And then friction we're mostly familiar with. Okay, the force of friction is going to be capital F with the lowercase f. These are subscripts, by the way. They go down a little bit below the line. And then the applied force is capital F and an uppercase A. Sometimes it's a lowercase a. And lastly, the normal force, which tends to confuse people, we'll spend a little bit more time on this one, is capital F with a capital N subscript. Okay, yes, you have to draw the picture. Let's talk for our first off about the gravity and the normal force. These two forces frequently are paired together because they often tend to work against each other. Now, let's imagine for a second that you have a little man, and the little man is standing on the ground. Yes, you have to draw the little man. So if the little man is standing on the ground, I'm going to draw in the force of gravity, and I'm going to do that by just taking my pen and I'm going to draw an arrow going down because gravity always works downward, and I'm going to label this FG for the force of gravity. Okay. Now, if that were the only force acting on our little man here, then this guy would be falling. The earth would be pulling him, and he would be changing his motion, because that's what forces do. They change motion. But he's not changing his motion. He's just standing. He's standing on the street or on the sidewalk. So if he's not moving, there must be some other force that's keeping him from falling. And we call that force the normal force. And the normal force is in the opposite direction. And so if we look at the normal force and the size of it, and the size of the force of gravity, we can see that the arrows are the same length, and the arrows are in opposite directions. So these forces are what we call balanced. And if forces are balanced, it means that there is no change in motion. And that means that our little man is not going to be falling. He's not going to be changing his motion at all. He's just going to just stand there on the street side. Let's do one other little experiment with our little man here. And yes, you have to copy this new picture. So here we have a new little guy, and this guy is trying to stand up. Instead of on the sidewalk, he's trying to stand on water. And what is going to happen to the little man that tries to stand on water? So let's draw the forces that will act on him. First we have the force of gravity. And gravity will pull him down toward the center of the earth. And the water will push back. The water has what we call a normal force. The problem is that the water can only push back a very, very small amount. You know, water can support maybe like a little bug, like a little water strider, or maybe a leaf that's just barely floating on it, but it can't really support a person. So notice that the normal force provided by the water pushing the man up is way smaller than the force of gravity. And so in this case, we have forces that are unbalanced. And unbalanced forces will cause the object to change motion. And in this case, the object is going to move in the direction of the greater force. So if that's not going to be the normal force, because the normal force is smaller, so it's going to be the force of gravity. So in this case, our little man will sink. Okay, here he goes. Blah, 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 blah. Moving down because of the force of gravity. Okay, our last two forces are going to be friction and the applied force. These are often paired together because they very frequently work against each other, just like the normal force and gravity work against each other. Yes, you have to draw this picture too. Okay, so here we have a man who is pushing a refrigerator, okay, something that's kind of heavy. And so what I want to do is I want to draw a diagram of the two forces that are going to be on the refrigerator. We're focusing on the refrigerator. And so on the refrigerator we are going to have, first off, so we're going to have two forces on the refrigerator. The man is pushing the refrigerator to the right. We call that the applied force. He is applying a force or a push on the refrigerator. So he's pushing it to the right. Now let's imagine for a second that the refrigerator isn't moving. He's pushing really, really hard, but for some reason it won't go. And so the refrigerator is pushing back to the left. And the reason why the refrigerator is pushing back is because of friction. Friction is keeping the refrigerator from moving. And these two forces are in opposite directions. And you notice that they are the same length, the same magnitude, the same size. And so they are balanced. And remember that when forces are balanced, that means that there is no change in motion. And if the refrigerator is not moving and the forces are balanced, the little man is pushing, but the friction is pushing back, then there's going to be no change in motion. Okay, write that down. Okay, now let's imagine that the little man trying to push the refrigerator, he pushes really hard, and applies a huge applied force to the refrigerator. Okay, now what's going to happen, you'll see that the applied force is larger than the frictional force. They're still in opposite directions, but one is much greater than the other one. And so what is going to happen is that the applied force is going to cancel out the frictional force, and the object, because the applied force is more, the object will begin to move in the direction of the net force. So in this case, the refrigerator is going to start moving to the right because the applied force is unbalancing the frictional force. So when we have unbalanced forces, we get changes in motion. Now the refrigerator will begin to move. Okay, I'd like to do one more example with you. Let's take an airplane. So this time we're going to draw our airplane again. All right. Okay, so there's our airplane, and our airplane is flying off to the left. And so what I want to do is I want to just draw a force diagram and just label some of the forces that are going to be acting on the airplane. First off, we have the force of gravity. And what direction is that going to be? And that is going to be down. So yes, you have to draw the airplane, and let's draw a arrow going down. We have the force of gravity. Now, I want you to imagine that the airplane is just flying straight and level. It's not speeding up, it's not slowing down, it's not changing its motion at all. And if it's not changing its motion, that means that all of the forces acting on the airplane have to be in balance with each other. So if there's a force of gravity pulling the airplane down, there has to be a force lifting the airplane up. Now, the airplane isn't sitting on the ground, so there's no normal force. In this case, we have what's called the force of lift, and I'm going to abbreviate that capital FL. And this is the lift of the airplane that's created by the air flowing over the wings. Okay. To make the airplane go to the left, we have to have our applied force. This is usually given by the engines or the jet engines or the propellers or whatever it is. And then if that force, if the plane isn't speeding up or slowing down, it's flying at a constant speed, that has to be balanced just by the frictional force. And in this case, the frictional force is going to be the force of the air friction. And all of these forces, the applied force, the frictional force, balance each other, the lift and gravity balance each other, and that's what allows the airplane to continue to fly in a straight line with no changes. Okay, so there's a force diagram for you, and I hope you learned something about forces and diagrams and how to represent them with arrows, and hope you have a great day.